Hi guys, hope you're having a good day. Remember, we are going to skip the first set of notes that you come to, the section 4 talking about evidence for the Big Bang, and we're going to jump to the Doppler effect. And the colored words are the ones that you need to write down in these notes. So, scientists know that galaxies are moving away from us, that the universe is expanding, but how exactly do we know that? And it's because of this thing called the Doppler effect. So before we can understand galaxies, we need to figure out what the Doppler effect is and how it relates to things that we already know. So in order to understand that, we need to rewind back to 8th grade when you guys talked about waves. And hopefully all of these words sound familiar to you. Remember, you have a rest position, and that's what this green line is here. And the rest position of the wave would be like if the wave wasn't moving at all. But once we get it started moving, we measure how high the wave is with something called the amplitude. And then the high parts are crests, and the low parts are troughs. Now, the thing that we really care about today is the wavelength. And the wavelength is the length of the wave. Pretty easy. So this first one shows you from crest to crest. We measure the length of the wave, but it doesn't have to be that. It could obviously be trough to trough, but it could just be a random point in the wave to the exact same random point on the next wave. So wavelength corresponds to frequency. The frequency of the wave is equal to the number of waves that pass a particular point in 1 second. So if we take a look at this box here and assume that we captured 1 second worth of time and all of these waves were allowed to travel, which one would have the highest frequency? Hopefully you picked this bottom one right here. This has the most waves that pass through this point in this 1 second. Now, the trade-off with having a high frequency is that you have a very short wavelength. Look at that wavelength compared to this one here. This one's much longer, but that's because that guy has the lowest frequency. So now that we remember a little bit about waves, let's talk about this Doppler effect. So we're going to talk about it in two situations that we've seen before, in water and in sound. So water's pretty simple. You guys have all seen something not moving in water, and it sends off waves in these concentric circles here. So for this, we got a bug that's right in the middle of the water. He's not moving in any direction. So because of that, if you are at point A or point B, you have the same frequency and the same wavelength. But now if this bug starts to move, what's going to happen is he's going to scrunch up all of the waves on the side he's moving towards, and the ones on the opposite side get spread out more. See how these guys are more spread out and these guys are more squished? Now what happens is the person sitting at point B has a higher frequency of waves and therefore a shorter wavelength. That is the Doppler effect. Now, another one that you guys have heard before is sound. So if we picture a fire truck and he's moving, he's going to squish these waves up in the direction that he's moving, and these ones are going to spread out on the opposite end. So what happens is when you squish the waves like that, you change their frequency, and you end up changing their pitch, and we can actually hear a difference in sound. So when the fire truck's moving towards it, it has a really high-pitched sound, and the second that it gets away from us or starts traveling in the other direction, we hear a different change in tone. Let's fast forward a little bit. So it's coming towards us, and we hear that's a pretty high-pitched sound. And you hear the second that it passes us, it totally changes what it sounds like. And this is an example of the Doppler effect in sound. So we've talked about water, we've talked about sound. Let's finally talk about light. Light is also a wave. It's an electromagnetic wave. And the same thing happens. If light is moving, if it's moving towards you, it's going to scrunch up all of the waves where it's moving towards you, and it's going to spread out all of the waves when it's moving away from you. Now, in order for this to happen, light has to move incredibly fast, and we have not seen this on Earth, but it happens in our galaxy. Light has different wavelengths, and those different wavelengths determine what color we see. So the two that I'm really going to focus on today are red and blue. And if you notice, they are on opposite ends of this spectrum right here. Red has a pretty long wavelength, and blue is pretty short. Okay? So in light, like we just talked about, red has the longest wavelength, which means it has the lowest frequency. So less waves can pass in a certain time. Where blue is on the opposite end, blue's way over here, has a much higher wavelength, so that means it has a higher frequency. These waves are much shorter right here. So, what does this have to do with anything? How can we tell that the universe is expanding or that stars are moving away from us? It has to do with their color. So we need a way to see their color. And when elements burn, they don't give off every single color. They give off specific wavelengths depending on what element we have, and we can use a specialized tool called a spectroscope in order to see those. And this is what a spectroscope looks like. It basically takes light and it funnels it into a nice tiny little space. And then in a prism, it splits those wavelengths up. And then we pay attention to which ones are split up. So we know that stars are made up of mostly hydrogen and helium. So those are the only two elements we're going to focus on. When hydrogen burns, it gives off 4 wavelengths of light. Now these 4 wavelengths of light combine to this guy that we see right here, but the spectroscope breaks them apart. We have this red, green, blue, and the indigo that we have going on. So here's an actual picture of it. This is hydrogen in a lamp, and then these two things right here are what the spectroscope sees. And you can tell there's that red, there's a green, a blue, and the indigo that we have in there. Now helium's a little more complex. Helium burns 9 wavelengths of light. You can tell that some are brighter than others, like this yellow is way brighter than these ones over here. So guess what color it looks like to us? It's pretty yellow. Here's a picture of it actually doing it again. You can see all these different ones, and you see how much brighter yellow is right here. So let's try to put all of this together. Remember that light waves that travel towards us have a higher frequency. This is traveling towards us. Than light waves traveling away from us. The waves get spread out. So we have these spectrums right here of what we see, and here's just like a line in the middle that's showing us where the middle is. Now if the thing giving us light is a star or a galaxy, and it's staying still, this is what we would expect it to look like right here. But if it's moving, it's going to shift the way that the light is viewed. So an increase in frequency is called a blue shift, meaning we can see this line get shifted towards the blue end of the spectrum. This is the red end of the spectrum. And when this happens, you can see that these waves get squished together. That means that it is moving towards us. Now remember, this isn't meaning that it's just the blue stars that are moving towards us. It means that the shift in the light we see is towards the blue end of the spectrum. And as you probably guessed, red is exactly the opposite. If this is like, our reference point right here, and it gets shifted this way towards the red end of the spectrum, that means that this galaxy or this star that we're looking at is moving away from us because those wavelengths are being spread out. So, how can you remember this? You guys know those really obnoxious lights that people have in the front of their car? If you see blue lights, it means something's coming towards you. And if you see red lights on a car, it means that it's moving away from you. So, nice, easy way to remember it. Blue is coming towards, red's moving away. So, let's pretend that we have this hydrogen spectrum that we have going on right here. We know that this is what stars are made of, is hydrogen. If light is traveling towards us, remember, that's blue, all of the lines are going to shift towards the blue end of the spectrum. So this red isn't going to be here anymore. It's going to shift. This green is going to shift. The blue and the indigo are going to shift that way. This is what a blue shifted hydrogen spectrum would look like. You can see that they move towards the blue end of the spectrum. Now it's still hydrogen. We're still seeing all of those colors, but they're moved a little towards the blue. Where if something's moving away from us, remember we see the red lights on the car, you would expect everything to move towards the red end of the spectrum. And that's exactly what happens. Everything shifts a little more this way. So, let's test ourselves. Let's say that we got a star and it's only made of hydrogen. Here is the normal spectrum, right here. And this is what scientists see. Now first you need to figure out, is it a red shift or a blue shift? And then figure out what direction that is. So hopefully you said a red shift. It's moving towards the red end of the spectrum. And red, remember, means that it is moving away from us. Think like red taillights. So now let's say we got a star that's made up of just helium. This is what the normal helium spectrum looks like. And this is what scientists are seeing. Now, hopefully you said that this is moving this way, which is towards the blue end of the spectrum. So that means that it is moving towards us. Think blue headlights are coming towards us. All right, here's another one. The star is also made of helium, and here's the normal helium spectrum for reference. What way do you think the shift is? Now, this one's a little harder to see because it kind of changed colors on us. But remember, if yellow shifts over enough, he's in the orange category. Red shifted off of our little table here, and this thick line of green right here kind of changed to more of a green and less of like a teal color. So this shifted towards the red end. That means that it is moving away from us. Now, we know that most stars are made up of both hydrogen and helium. So here's hydrogen and helium together. This is what a spectroscope would show us of most stars. And then we got a star's data. So what shift is this? Hopefully you said redshift. It shifted towards the red end, so that means that this star would be moving away from us. All right, last thing we got to talk about. The more shifted the spectral lines are, the faster that the star is moving. So more redshift means more distance away from us. So both of these are redshifted. Both of them have moved towards the red end of the spectrum. But which one would you say is traveling the fastest? Hopefully you said star B. He's moving a little more towards the left. These ones are shifted a little more than what they started with. So all of these are red shifted. Which one would you say here is traveling the fastest? Woohoo! Most shift means it's going the fastest. This one shifted so far that the red is like right on the edge of our spectroscope lines. So what I would like you guys to do today, and then you are done with this note section, is when it says color your own, I want you to color these lines for hydrogen and helium. And then I want you to try your own redshift and blue shift underneath those. All right, so the last thing I want you to do is on this worksheet right here, I want you to get all of the data on here and then actually graph it on the next page. So the data is kind of hidden in this paragraph form. So they did the first one for you. It's object M60, so they put that down here. Its speed is 1,117. And then it's 55 million light years away, so they put that here. So get this table filled out, get this graph filled out, do not need to answer any of the questions, and we will talk about this tomorrow. Enjoy your day.